Hello students, today we will continue this chapter chemical equilibrium. So we start with the applications of equilibrium constant. The applications of equilibrium constant. The first application is to predict direction of a reaction. You know that the equilibrium constant Kc equal to concentration of C raised to C into concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to B. Okay. Where all concentrations are equilibrium concentrations. Now the ratio is called reaction quotient, QC. When the concentrations are not necessarily equilibrium concentration. So it is denoted as QC, that is reaction quotient, and it is also equal to concentration of C raised to C into concentration of D raised to D divided by concentration of A raised to A into concentration of B raised to B. Now this expression for Kc is for this general reversible reaction. A plus BB gives CC plus DD. Now there are three possibilities. Number one, if QC is less than Kc, means first graph, first figure, the reaction will proceed from left to right in forward direction, generating more product to attain the equilibrium. So this is the first case. If QC is less than Kc. You consider second case, second figure. Both are equal. Means if QC is equal to Kc, the reaction is at equilibrium. The reaction is at equilibrium and hence no reaction will occur. The second figure you can observe. The reactants and products are at equilibrium. And the third case is if QC is greater than Kc, the reaction will proceed from left to right, requiring more reactants to attain the equilibrium. So this is the third figure, third condition, where QC is greater than Kc. Now we'll discuss the second application of equilibrium constant. That is to know the extent of reaction. The magnitude of Kc is number one, directly proportional to concentration of product, and number two, inversely proportional to concentration of reactants. You can observe this figure. Suppose on the left hand side, the value of equilibrium constant Kc is very small, then reaction proceeds hardly at all. As the value of equilibrium constant increases, now if it ranges from 10 raised to minus 3 to 10 raised to 3, between this region, there is appreciable concentrations of both reactants and products. So both reactants and products are present at equilibrium if the value of Kc ranges from 10 raised to minus 3 to 10 raised to 3. Now, between this range, the larger the value of equilibrium constant Kc, the farther the reaction proceeds to the right before reaching the equilibrium state. as here value of equilibrium constant increases, if it is very large, if the value of equilibrium constant is very large, then the reaction proceeds nearly to completion. Is it clear? The third application is to calculate equilibrium concentrations. An equilibrium constant can be used to calculate the composition of an equilibrium mixture. So this is where the applications of equilibrium constant. Now we'll see some problems. The equilibrium system is given as twice SO2 gaseous plus O2 gives twice SO3 gaseous. Was found to contain concentration of SO2 equal to 0.40 moles. Concentration of O2 is equal to 0.13 mole. And concentration of SO3 is equal to 0.70 moles. Find the value of Kc. The answers are given as A 12, B 23.6, C 9, and D 48. Now we have given this reaction. Which reaction? Twice SO2 gaseous plus O2 gaseous gives twice SO3 gaseous. Okay. Now at equilibrium, the concentrations are 0.4, 0.13, and that of SO3 is 0.7. Now we can write the expression for Kc for this reaction as Kc equal to concentration of SO3 raised to 2, that is square, divided by concentration of SO2 raised to 2 into concentration of O2. By substituting the values of concentrations in this expression, we can write as it is equal to 0.7 square divided by 0.13 into 0.4 square. If you simplify this, you will get the answer 23.6. The answer is B, 23.6. Now we'll see second example. The reaction is given as N2O4 gives twice NO2. If N2O4 is 25% dissociated in a 4-liter vessel at given temperature, what is the Kc for the reaction? Now here, the answers are given as A 1 by 16, B 1 by 4, C 1 upon 6, and D 1 by 12. We have given the reaction N2O4 gives twice NO2. Initially, reactant is suppose 1 mole. There will be no product initially. After some time at equilibrium, the number of moles we can write as set of reactants as 1 minus alpha and the products 2 alpha. And you can write the concentrations at equilibrium as 1 minus alpha upon 4 and 2 alpha upon 4. So you can write the expression Kc equal to and substitute the value as Kc equal to 2 alpha divided by 4 square divided by 1 minus alpha upon 4. If you simplify this, you will get as alpha is equal to 0.25. Now you know that K is equal to, now substitute the value of alpha. So you can write K is equal to 4 into alpha, that is 0.25 square divided by 4 into 0.75, that is 1 minus alpha. So you will get the answer as 0.25 into 0.25. Here you can cancel 4 and 4. So what is remaining? 0.25 into 0.25 divided by 0.75. That is 1 upon 12. So the answer is D, 1 upon 12. Is it clear? Now see exercise 3, third example. The example is given as calculate the equilibrium constant for the reaction. The reaction is given as H2 gaseous plus CO2 gaseous gives H2O gaseous plus CO gaseous at 1395 Kelvin. If the equilibrium constant at this temperature for the following are given as twice H2O gaseous gives twice H2 gaseous, twice H2O gaseous gives twice H2 gaseous plus O2 gaseous. The value of K1 is given as 2.1 into 10 raised to minus 13. Suppose this is equation number 1. And for the reaction, twice CO2 gaseous gives twice CO gaseous plus O2 gaseous. The K2 value is as 1.4 into 10 raised to minus 12. Suppose this is equation number 2. What will be the answer? A 3.26, B 4.28, C 1.34, and D is given as 2.58. Now the reaction is given as twice H2O gaseous gives twice H2 gaseous plus O2 gaseous. This is the reaction. The value of K1 is given as 2.1 into 10 raised to minus 13. Suppose this is equation number 1. And the second equation is twice CO2 gaseous gives twice CO gaseous plus O2 gaseous, and the value for K2 is 1.4 into 10 raised to minus 12. Suppose this is second equation. Now subtract equation second from equation 1. You will get twice H2O minus twice CO2 gives twice H2 minus twice CO. So K is equal to K1 upon K2. Therefore, twice H2O plus twice CO gives twice CO2 plus twice H2. Suppose this is equation number 3. Now divide equation number 3 by equation number 2. You will get H2O plus CO gives CO2 plus H2, and K dash equal to square root of K. So CO2 plus H2 gives H2O plus CO. K double dash equal to 1 upon K dash. Now K double dash equal to K upon K dash. So that is equal to 1 upon square root of K, that is equal to square root of K2 by K1. You substitute the values of K1 and K2. So you can write as square root of 1.4 into 10 raised to minus 12 divided by 2.1 into 10 raised to minus 30. If you simplify it, you will get the answer as 2.58. We'll see the next problem. The equivalent quantities of HI, H2 and I2 are brought to equilibrium. if the total pressure in the vessel is 1.5 atmosphere and Kp for the reaction, that is twice Hi gaseous gives H2 gaseous plus I2 gaseous, is 49. Which of the following is the correct value for the equilibrium partial pressure of I2? The answers are A 0.4, B 0.9, C 0.7 and D 0.5. We'll see the solution for this example. The reaction is given as twice Hi gives H2 gaseous plus I2 gaseous. Initial pressure is P. The final pressure here will be P minus 2x, here P plus x and here P plus x. Now 3P is equal to 1.5 atmosphere. Therefore, P is equal to 0.5 atmosphere. Now, in bracket P plus x square divided by P minus 2x square is equal to 49. Now here Kp is equal to Kc as delta Ng is equal to 0. So P plus x is equal to 7P minus 14x. That is 15x equal to 6P. So x equal to 6P divided by 15, that is equal to 2 upon 5P. Therefore, x equal to 2 upon 5 into 0.5, that is equal to 0.2 atmosphere. Therefore, I2 is equal to P plus x, that is equal to 0.7 atmosphere. Is it clear? Now we'll discuss the next example. Number 5. In the following gaseous equilibrium, P1, P2 and P3 are partial pressures of X2, Y2 and XY2 respectively. X2 plus twice Y2 gives twice XY2. Here P1, P2 and P3. The value of Kp is A 2P3 upon P1, P2. B P1, P2 in bracket P3. C P3 square divided by P1 in bracket P2 square. And the last one D in bracket P1 in bracket P2 square divided by in bracket P3 square. Now we'll see the solution of this problem. We have given the reaction X2 plus twice Y2 gives twice XY2. This is the reaction. And here pressures are P1, P2 and P3. We have the expression Kp is equal to for this reaction as Kp is equal to in bracket P3 square divided by P1 in bracket P2 square. That is the answer. Next example. 60 ml of H2 and 42 ml of I2 are heated in a closed vessel. At equilibrium, the vessel contains 28 ml of Hi. Calculate percentage of dissociation of Hi. Now, at constant temperature and pressure, moles are proportional to volume of gas. The reaction is H2 plus I2 gives twice Hi. The initial moles of H2 are 60, that of I2 is 42, and initially no product is there. At equilibrium, you can write as 60 minus x for H2. For I2, you can write 42 minus x. And for product Hi, you can write as 2x. And here 2x is equal to 28 given. So here x will be equal to 14. So here 60 minus x is 60 minus 14, that is 46. And 42 minus x, that is 42 minus 14 equal to 28. Now, you know that for this reaction, you can write Kc equal to, in bracket, 28 upon 1 square divided by 46 upon 1 into 28 upon 1. That is equal to 28 by 46. That is equal to 14 upon 23. Again, for this reaction, initial moles at equilibrium, number of moles where alpha. What is alpha? It is the degree of dissociation. Now K dash C equal to, you can write as alpha square divided by 4 in bracket 1 minus alpha square, and 1 upon K is equal to 23 upon 14. That is equal to alpha square divided by 4 in bracket 1 minus alpha square. On solving, you will get alpha equal to 0.719 or 71.9%. Now we'll see the next example, number 7. The percentage of dissociation is 0.4 at 400 Kelvin and 1 atmosphere for the gaseous reaction. PCl5 gives PCl3 plus Cl2. Assuming ideal behavior of all the gases, calculate the density of equilibrium mixture at 400 Kelvin and 1 atmosphere. Given observed molecular mass at equilibrium equal to 148.92. Now we'll see the solution for this example. We are given the reaction PCl5 gives PCl3 plus Cl2. Initial moles you can write like this, and moles are at equilibrium will be 1 minus 0.4 and here 0.4 and here also 0.4. The total moles are 1.4. Now you know that PV is equal to W upon M RT. This expression we have got from general gas equation, that is PV is equal to nRT. Now at equilibrium, density D is equal to Pm upon RT. By substituting the values, you can write as it is equal to 1 into 148.92 divided by 0.0821 into 400. We will get the answer 4.53 gram per liter. Okay. Next example, number 8. The reaction is given as N2 plus thrice H2 gives twice NH3. Now Kc for the reaction is 0.5 mole raised to minus 2 liter square at 400 Kelvin. Find Kp. Given value of R equal to 0.082 liter atmosphere per degree per mole. Now we'll see the solution for this example. You know the relation between Kp and Kc is Kp is equal to Kc in bracket RT raised to delta N. Delta N for this reaction is minus 2. So you can write Kp is equal to 0.5 divided by 0.0821 into 400 raised to 2. By solving this, you will get the answer as 4.636 into 10 raised to minus 4 atmosphere raised to minus 2. Next example, number 9. For the reaction, twice HI gives H2 plus I2 at equilibrium 7.8 gram, 203.2 gram and 1638.4 gram of H2. I2 and HI were found respectively at equilibrium. Calculate Kc. Now for this reaction, twice HI gives H2 plus I2. You can write molecular weight of HI 128, that of hydrogen 2, and that of I2 is 254. So at equilibrium, you can write as 1638.4 divided by 128. For H2, 7.8 divided by 2. For I2, 203.2 divided by 254. So you will get it is equal to 12.8, here 3.9 and here 0.8. As a delta N for this reaction is 0. So Kc is equal to concentration of H2 into concentration of I2 divided by concentration of Hi square. By substituting the values, you can write as in bracket 3.9 into 0.8 divided by 12.8 square. So you will get the answer finally as 0.019. Next example number 10 as 0.5 moles of H2 and 0.5 moles of I2 react in 10 liter flask at 448 degrees centigrade. The equilibrium constant case is 50 for H2 plus I2 gives twice Hi. What is the value of Kb? And calculate moles of I2 at equilibrium. Now you know the relation Kp is equal to Kc in bracket RT raised to delta N. Delta N is 0. So Kp equal to Kc, that is equal to 50. And for this reaction, initial moles of 0.5, here 0.5 and initial no product, that is 0. Finally 0.5 minus x, 0.5 minus x, and here 2x. So you can write as in bracket 2x square divided by 0.5 minus x into 0.5 minus x, that is equal to 50. By simplifying, you can write it as 2x divided by 0.5 minus x is equal to 7.07. Therefore, x is equal to 0.39. Moles of I2 at equilibrium is equal to 0.50 minus 0.39, that is equal to 0.11 mole. Okay. Thank you.